Good morning, dear students. Today we are going to start the new topic, which is electric resonance circuit. First of all, the meaning of resonance. What is the meaning of resonance, and in what conditions and on what objects it is being applied? Basically, resonance can be understood in case of objects which are oscillating with its own frequency, right? For example, if I talk about a swing, in that case a child is swinging and with its own frequency, and when another child comes and push him in the same direction, then in that case the amplitude of that swing increases. So we can say that resonance might have occurred. Second example, we can consider oscillating bodies, like suppose pendulum. Okay, so in that case, suppose the pendulum is oscillating at its own frequency like this. Okay, and after some time you come and you just pull it and give its own new frequency, then you will observe that the amplitude of oscillation has been increased. So we can say that resonance have been occurred. So basically, resonance basically means when any object is imposed with any frequency such that its amplitude increases, then we can say that resonance might have occurred. Now we are having two kinds of electric resonance circuit, that is RLC series resonance circuit, and another one is RLC parallel resonance circuit. This is parallel resonance circuit. Okay, in this video we will discuss about series resonance circuit, and parallel resonance circuit will be discussed in the next video. Series resonance circuit, a circuit in which resistance R, inductor L and capacitor C are connected in series, and the circuit admits maximum current at resonance. Okay, at resonance, then that is known as series resonance circuit. Now we have studied in the previous videos that in case of series resonance circuit, the impedance of the circuit Z is given by root of R square plus omega L minus, this is omega L minus 1 upon omega C whole square. Okay, where omega L is what? At very low frequency. This is this is known as inductive reactance, and this is known as capacitive reactance, such that XL is equal to omega L and XC is equal to 1 upon omega C. Now that can be written as omega is 2 pi nu L, and similarly XC can be written as 1 upon 2 pi nu C. Okay, now from this we can say that at lower frequencies the value of inductive reactance is lesser, since nu is less, while capacitive reactance is more, right? For example, lower frequency, suppose if nu is 0, XL is 0, it is having lower value, and at value nu is equal to 0, X is equal to infinity. So we can say that at lower frequencies XL is less while XC is having higher value. Similarly, we can say that at higher frequencies XL is higher and XC is lower. It means when we go on increasing the frequency from lower to higher value, the value of XL goes on increasing while the value of XC goes on decreasing. Okay, this is the point. When we increase the frequency from lower to higher value, the value of XL, which is initially less, it goes on increasing while XC goes on decreasing. So at particular frequency, when we can say XL is equal to XC, at a point when XL is equal to XC, right? So in that case, we can say the resonance must have occurred. If a point will reach at which XL is equal to XC. So in that case, we can write omega L is equal to 1 upon omega C, or this is omega square 1 upon LC. Now omega can be written as omega R square is equal to 1 upon LC, where omega R is known as angular resonance frequency, and this can be written as 2 pi nu R, which is equal to 1 by LC whole square. This is whole square. So we can have this as square, taking square root, we will be having 2 pi nu R, which is equal to 1 upon root LC, or nu R is equal to 1 upon 2 pi root of LC. So this is known as resonance frequency. Means at that frequency we can say that inductive reactance is equal to capacitive reactance, and also in that case this omega L is equal to 1 upon omega C. So the fact is we will having Z is equal to R. Means the resistance of the impedance of the whole circuit is reduces. Since Z reduces, resistance reduces, it means it will admits the maximum current to pass through it. As we know that current I naught is equal to E naught by R. Okay, and in case of RLC circuit, we will write here E naught by Z, which is equal to E naught by R. Right, since if R is less, in that case current will be maximum. If R is more, value of resistance is more, current is more. So we can have clear understanding that in case of series resonance circuit, the circuit will admit the maximum current at lower resistance values, at resonance values, and since it is admitting the maximum value of current, this is also known as acceptor circuit. Okay, series resonance circuit is also known as acceptor circuit, and we can say that this circuit is purely non-inductive resistive circuit. As omega L is equal to omega C, we are having only R component. Okay, so in that case we can say that current and voltage at the series resonance circuit will be in same phase. Since Z is equal to R, and circuit is non-inductive, in that case we can say that current and voltage are in same phase. So this is all about the series resonance circuit. In our next video we will study about the parallel resonance circuit.